Thanks, it's great to be here. Had a fun first day, lots of fun conversations. As John DeGo said, I'm Mike Stay. I'm the CTO of Pyrofex Corporation here. We employ about a dozen Scala developers. We would like to hire about 10 times as many. We found that anyone who can handle the problems that uniting object-oriented programming with functional programming produces is an excellent candidate for hiring. We've really enjoyed the interview process that we've gone through with these people. We have an excellent team, and we're growing quickly. So if anyone is interested in that, feel free to contact me later. The ARChain Cooperative hired Pyrofex to design and build their new blockchain. Greg Meredith is a friend of mine. He's the president of ARChain, and he approached me and my business partner Nash Foster with the idea that we would help them find the developers they needed in order to produce Greg's vision of what the blockchain should be. Now, Greg is an avid supporter of Pi calculus. Pi calculus itself is not a functional programming language. So the immediate question is, how then can we reason about the behavior of Pi calculus? How can we reason about the behavior of these smart contracts written on this blockchain and have any confidence in what they're going to do? The whole platform is written in Scala. He gave us the high-level architecture and a variant of the Pi calculus he called the row calculus. The word calculus in this context means programming language. The original meaning of calculus is from Latin, and it means pebble. It's used for counting things, like how many cows and sheep you've got. Eventually, it came to mean a specific method for solving some mathematical problem. And so the first place that most people hear of calculus is in high school, where they talk about the differential and the integral calculus. Right here, we've got Leibniz notation for the derivative of the ratio of two functions. So one of the things Leibniz said was that if you've got the right notation, then thinking about the problem becomes enormously easier. So the use of the word calculus that you'll hear throughout computer science talks has to do with both the notation of the language that they're using for solving the problem and the method of applying that notation. This is the row calculus. I won't go into it now, but this is the language that Greg Meredith and Matthias Radestock put together. One of the things to notice there is that it's got here and here, we've got evaluation and serialization. So it is a reflective calculus. It lets you look at the structure of the terms. The other thing is that unlike many programming languages, the state of the computer is entirely represented in the terms. You don't have a heap, you don't have a stack, you don't have consoles, you don't have any of that other stuff going there. The entire state is represented here. And so if you can reason about the transitions between states, you can reason about how the entire computer is going to behave. To understand a language like Golang, we have to go back about 90 years. This is David Hilbert. He's a German mathematician. He's often ranked among the top 10 mathematicians of all time. Right here we've got the Wikipedia page, things named after David Hilbert. There are about 46 of those. In 1928, David Hilbert posed a problem. Now, Hilbert's program, yes, right here. Hilbert's program was this idea that if you could express a problem mathematically, perhaps you could solve it mathematically. Now, Leibniz had that idea. He talked about his universal language. But by the time Hilbert had come along, there's a whole bunch of work in logic. People were beginning to be able to write down these things, make connections between logic and numbers. So it wasn't as ridiculous as an idea as we might think now. that given a mathematical statement of any problem, if we can encode it using mathematical language, perhaps there's some way that we can process that mathematically and figure out what it was. Now, Gödel in 1931 proved that his grand vision couldn't work. He used some tricks about encoding mathematical statements as numbers. So that if statements talk about numbers, they might also talk about statements themselves, and then you get paradox, that sort of thing. And by constructing a paradox, he showed that there were certain things that you couldn't solve. But it was this very complicated, weird sort of construction, and people still held hope that for practical problems, perhaps there was a way to still do it. So Hilbert's decision problem, the Entscheidungsproblem, was the question, is there an algorithm that takes a statement of first-order logic and decides whether it is universally valid? That is, whether it holds in all the different models, whether it follows directly from the axioms and rules. So to solve the decision problem, first you have to define what you mean by the word algorithm. There weren't computers at the time. All of the computation people had done was sort of on an ad hoc basis. Computer was a job description, not the name of an object. And so in 1934, 36, a young Englishman named Alan Turing described a machine that we would now call a general purpose computer. By using self-reference in a way very similar to the way the paradox says this sentence is false, Turing showed that if he assumed that there was a program to solve Hilbert's decision problem, then he could construct a problem that he could prove both had to stop and had to run forever. So because the only assumption he made was that there was a way to solve the decision problem, and deriving this contradiction, he was able to show that the decision problem itself couldn't be solved. When he went to publish his results, he found that this guy beat him to the punch by just a couple of months. This was an American logician named Alonzo Church. Alonzo Church published effectively the same solution just a few months earlier. So Church used what we would now call a statically typed, lexically scoped functional programming language. He called it the Lambda calculus. Turing went on to show that anything Lambda calculus could compute, Turing's computers, his machines could compute, and vice versa. Since Turing's formulation of computation was very mechanical, his approach dominated the fledgling field of computer science for the next 30 years. So he was, famously instrumental in setting up the code-breaking effort at Bletchley Park, actually building these computers that would do practical problems. Because his ideas about computation were very machine-like, they were easily adapted to machines. And the hardware that was available at the time had to be built and wired by hand, and special purpose machines for solving these problems. It was only once computers became powerful enough to write compilers that people began to rediscover Church's ideas. And I've heard it said that the history of programming languages is the gradual rediscovery of Lambda calculus. In math class, we all learned about functions. You get something like f of x equals 3x squared plus 2. Right? And then we're asked to evaluate this function at 5. So everywhere an x appears in the expression on the right, we substitute the value we were given on the left into it, and then we simplify the expression. When we write down symbols, the rules about the way symbols can go together is called syntax. In English, a proper English sentence has to start with a capital letter and end with a period. If you don't do that, it's a syntax error. In high school algebra, a function definition has to have a name, here it's f, has to have an open paren, has to have a comma-separated list of variables, a closed paren, an equals, and an algebraic expression that has its own syntax. If it's not written that way, it's not a valid function declaration. Syntactical rules don't talk about meaning, but rather about what symbols are allowed to go together. The syntax of the Lambda calculus is very simple. It has 3 different syntactic productions, or terms. We've got variables, x, Lambda x dot t is called abstraction, and t can be anything in there, again, recursively. And because this was fairly old, lambda x dot t here, thank you. Lambda x dot t means the same as f of x equals t. It's just an anonymous function. And then t of u is application. So as we saw, f of 5, that's the same sort of thing. So this was, from the beginning, intended to model what we know as functions. Now, I haven't written down anything about types here, but the intended semantics of lambda calculus was that a type is a set of values, a variable is a place where substitution occurs, an abstraction is a function from one set to another one, and an application is a place where you take some other value and substitute it in. Even though Turing machines compute the same class of functions, lambda calculus makes it much easier to reason about the meaning of a program. Turing machines and lambda calculus both describe a model of computation where you turn on the computer, you feed it a problem, you let it run until it's done, and then you collect the results. But 30 years after Turing's paper, the Advanced Research Projects Agency got funding to develop a network of computers. The ARPANET allowed computers to cooperate on solving problems by exchanging messages. The ARPANET served as a backbone for the growth of a larger network, and when the National Science Foundation got funding to build a better backbone for this network, ARPANET was shut down and the internet was born. It was the year 1990, same year that the first Haskell report was published. Robin Milner was a British computer scientist, worked at Cambridge. In 1991, he won the Turing Award, so not a slouch. During the 1980s, he was looking at this new way that computers were interacting with each other and thought that neither Turing's model nor Church's really captured this essence of computing by exchanging messages. So whereas a lambda term very clearly denotes a function that always gives the same output for a given input, a system that involves messages being passed around can behave very differently depending on the order in which messages arrive. It matters very much whether you have an empty bank account and a withdrawal or a deposit comes in first, right? We really want one to happen before the other, but have to be able to reason about both of those possibilities. There are also no clear input and outputs to a system like this. Just a continuous exchange of messages internally on the network and a continuous interaction with peripherals like keyboards and mice and disk drives and so on. Milner proposed and analyzed a series of calculi, and the culmination of these was a family of calculi known as pi calculi, where pi is a mnemonic for process. This is the syntax of the asynchronous pi calculus. There are 6 operations, each of which do some very simple thing. We've got nil that does nothing. P par q, that pipe symbol is pronounced par, means do P and Q at the same time. It's not feed one into the other, it's have them both running on the same computer at the same time. New x in P creates a new channel and calls it x, and then does P, which may refer to x inside. This isn't the original syntax that Milner used, but it's the one that we're using in Rolang. X bang y1 through yn says send a tuple of names y1 through yn on the channel x. So the only thing that's being passed around aren't data types, aren't data values. They're just these channels on which you can send and receive other tuples of names. The next line there, for y1 through yn from x, do P. So that reads an n tuple from the channel. You can think of this channel as being something like a table in a database. The send inserts a row. The receive pulls a row out and binds these variables to the values in the row. And then P is the processing that happens on those. replicate P means do P infinitely many times in parallel. Now, usually it's not implemented as actually spreading out infinitely many processes at once, but rather replicate P is the same as replicate P par P. So as that expands over and over again, you can produce as many copies of P as you need. So the lambda calculus can be embedded into the pi calculus. Yeah?
What's the meaning of names here?
So names are channels. I'm sorry, I tried to pull out all the use of name here. Name and channel is synonymous in this context. Thank you for clarifying that. I guess I missed this one. So you can embed lambda calculus into the pi calculus. It's something fairly similar, for those who know it, to the continuation passing transform, continuation passing style transform, where you, instead of returning a result up the stack, you invoke a continuation with the result, and it does something with what happens. So in this case, you would send the result on a channel, and that channel would have some process listening on it for what to do with the result. In the pi calculus, we can have race conditions. Here we've got one thing that's trying to read and two messages that it could possibly read. So there are two different reductions. This is not confluent like the lambda calculus. There are two different, fundamentally different ways that this can reduce. One is that it connects with the R there. And so it pulls out the R, substitutes it in for Y and P, and the S message is left over. The other one goes the other way around. Syntactically, they look very similar, but if R is a withdrawal and S is a deposit, again, these mean very different things. There are other variants of the pi calculus that have been found a lot more acceptance in the programming community than pi calculus itself. This one is taken from a Microsoft paper where they use something called the stochastic pi calculus. There, in addition to setting up channels and channels and processes that listen on those, you can also specify a rate on a channel. So we can only read every so often from that channel. And that lets them characterize chemical reactions, particularly biochemical reactions, and they've done models all the way from intracellular things, reactions happening within a cell, to intercellular, to intertissue, to all the way up to organ level models of biochemical processes, and have gotten much better results using this than with differential equation-based modeling. The other use that it's found is the SPI calculus, which is a pun on the word spy. It's all about encryption. You can see here that we've got public key and private key, we've got hashing, and so on. The SPI calculus lets you reason about cryptographic protocols, not about the fundamental underlying cryptographic primitives, but about the way you put them together. So if you assume the primitives work correctly, what else can you derive from that? And that's what the SPI calculus is used for. Now we get to the reflective higher order calculus. So this is a variant of the asynchronous pi calculus we saw earlier, in which the set of channels and the set of processes are mutually recursive. So we can see here, there's a star x, and there is an at p. Instead of the new and replication operations from pi calculus, we have evaluate and serialize. This ability to serialize makes the calculus reflective. It's possible for code to see the underlying structure of the channel that it's sending on or the channel that it has received over another channel. It also makes the calculus higher order, whereas in pi calculus, the only thing you can send around are names. In row calculus, you can send programs. You can send code over to some other process to execute and do with it as it will. Milner's intended operational meaning of pi calculus was clear. All of these things are pretty easy to understand what they're supposed to do. But because processes behave so little like functions, for a long time, nobody could give a clear denotational semantics for the pi calculus. Eventually, there was a researcher named Ian Stark who was able to give a denotational semantics in terms of something called functor categories. These are the categories, well, between any two sets, you've got a set of functions. Between any two categories, you have a category of functors. And so he was looking at these functors between categories and that category itself and taking semantics in there. It was all very complicated and hard to reason about from my perspective. And so then my question when Greg came to us and said, want you to use this variant of pi calculus is, how then can we reason about this if we can't say what it means? So one answer that we came up with was to stop trying to ignore the manner of computation. Here we've got two ways of doubling the number. One is adding it to itself, and we can see the carries being propagated down. You add the first 2 bits, put the carry bit up there, and continue, so on. The other one just shifts left, slides it to the left, and sticks a 0 on the front. These are two very different ways of calculating multiplying by 2, but they give the same answer, right? And the denotation of these two approaches is the same function. If we want to think about how something is computed, we can't drop that information anymore. And so we decided to use graphs. Each of these blue blobs here you could think of as a term in the calculus. And each of the red arrows is a way of going from one term to another one. We saw earlier that a particular term where you had 1 read and 2 writes could go in 2 different ways. Similarly, you can go back and forth between them, go all over the place in this graph. And then the question becomes, well, what then should a type mean? Is it a set? Well, makes sense if we've got this infinite graph of all the terms and all the rewrites between them, that a type would now refer to a subgraph. We're characterizing some part of this graph of the behavior of the language. Because we're looking at the terms themselves rather than a bunch of terms that are equivalent in some way, that mean the same thing, we can write down types that describe syntax. So that has been done in the past, and it's been called a structural type system. So in a structural type system, you have, let's see, did I put it there? No, not yet. I guess it's ahead here, yes. So in a structural type system, you have, say, this JSON structure. Name is Joe Schmo, age is 43, address 123 some avenue. If we want to characterize all the things of that kind, then we use the same syntax, but then instead of using a string like Joe Schmo, we use the type identifier string. So we're oscillating back and forth between syntax from the programming language, the terms themselves, the programs themselves, and syntax for types. So we've added together these 2 different ways of talking about terms. And so the subgraphs here, we can say, I want all the subgraphs that look a certain way, that are written down a certain way. And so the first line here, not nil and not nil, par not nil. This means that I want the terms that do something and can't be split up into 2 things unless one of them is nil. So this line says single-threaded. It's exactly the same concept as when we're talking about a prime number. Nil here is the monoidal unit operation in multiplication. In this case, it's the monoidal unit for par. 1 is the monoidal unit for multiplication. So this says, I want a number that's not 1, and it can't be factored into 2 parts unless one of them is 1. So 5 is a prime number. Why? It's not 1, and I can't factor it except 5 times 1 or 1 times 5. So the primes in this term language are the single-threaded programs. This next one here is a static firewall. What it says is, I want a program that's either nil or 2 copies of the same type running in parallel, or declares a variable and does that, or here either reads from something in the namespace open or writes to something in the namespace open. It can't read or write from anything that doesn't match this formula. So, firewall. We know it can only send and receive along these ports. This structural type system is sufficient to prevent all kinds of bugs. It lets us reason about which processes can communicate with which other processes, very much like the SPI calculus does. Another kind of type that we can do is called a behavioral type. Lets us talk about transitions between states. So I want all of the edges that match this particular pattern we're looking for. Luis Caires showed how to combine structural types that deal with resource usage with behavioral types into a single type system. It was something he built by hand. Acciai and Boreale applied his techniques to Pi calculus, so you can see a behavioral spatial type system for Pi calculus in their work. But ours, we derived algorithmically, and I'll show you a little bit of that later. This particular thing at the top, the xky, is the set of terms that for all terms u of type x and for all rewrites, rho, from t and u in a particular context k to some v, it must be the case that v is of type y. Now that's a mouthful. So next line, let's consider a specific case. In lambda calculus, we have this notion of application. We can take one term, apply it to another one. So this says, I want all those terms that when I apply it to a thing of type x, I get something of type y. Well, that's just the arrow type, x arrow y. So now this modality that's a behavioral type characterizes something in functional programming, but we can also apply it to the Pi calculus. Here, instead of using application, we're using the par operator. This says I want those terms that when I put them in parallel with something of type u. I'm not applying t to u or u to t. They're just running at the same time and then potentially interacting with each other. But I want those terms that when they're in parallel with something of type x, they always go to something of type y. So now this is a rely guarantee type, and Caires has this, explains that a bit in his papers. But now we can use something like functional programming to say this has to satisfy this property x. Whatever it is, maybe it doesn't leak, maybe it is firewalled in some way. Given something of this kind, I can guarantee that it goes over and turns into something of this other kind. So now we don't necessarily have functional behavior, but we have guaranteed characterizations of those behaviors that can be composed and reasoned about in much the same way that we can do that in functional programming. The DAO was a distributed autonomous organization. They were something like a distributed Kickstarter. They had gotten nearly $250 million, I think, 250 million roughly in their accounts. And then someone discovered a flaw in their wallet contract. There was a race condition. It was possible to check the balance to see if they could withdraw money and then get another message in before that withdrawal occurred. So if you flooded it with these withdraw requests, then all of them would say, yep, there's enough money in there, and then all of them would proceed. And he got $50 million out of the account of DAO, and fortunately they had set it up so that there was a 28-day waiting period, that he couldn't withdraw it and put it into his own account. It had to be held for 28 days. And during that month, there was an enormous amount of discussion in the Ethereum community, right? Do we roll this back? Do we stick our fingers in and alter the way this has been done? Or do we just say, hey, this was perhaps an unethical but totally valid way of interacting with the contract? Code is law. For a significant portion of the Ethereum community, they thought the whole point of the blockchain was that nobody could mess with it. So then along comes this and steals this, something like 30% of all the money stored in the blockchain. What do? So then Ethereum forked. We now have Ethereum Classic, where code is still law, and the hacker got away with it. And we have Ethereum, where it didn't happen. So then there's this question of how much is Ethereum Classic worth now compared to Ethereum, because all of a sudden all of the money doubled. It's like you suddenly open your wallet up and have 2 copies of every bill, but you can only spend one in one city and one in another city, right? So then what's the exchange rate between these 2 new kinds of bills? That was something they worked out. A more recent thing happened with the Parity wallet. Parity was a company that produced contracts for lots of different people to build up their own contracts on top of. This had a lot of nice features like multi-party signatures and waiting times and just a whole bunch of convenience features that were around holding the value. But they concentrated more on convenience than about security, and it turned out that a hacker was able to discover a way to delete the underlying Parity wallet. And so all of the other ones that had their money in them were still there. The money is still in those wallets, but it can't be removed. So it's there, but someone has fused the safe shut, right? And you can't get at it without blowing up the Ethereum network again. And while the DAO was early enough in the Ethereum community's growth that they thought, well, this one time we have to do this to save the network, otherwise nobody's going to use it. There's now an enormous amount of resistance to forking for the sake of these Parity wallet holders. At the time, the Ethereum was worth $380 million. These are the kinds of things that we can prevent using a type system. Solidity doesn't have a type system. We need types in order to reason about the behavior of our code. We as programmers, when we write code, are trying to express our intent on how the system should behave. But being human, we make mistakes. We screw things up. If we have a type system, that allows us to give a second, very condensed expression of intent. And then the compiler can compare the two and do all the tedious work of making sure that they line up. And if it ever finds a place where they don't line up, it says, I don't know if you screwed up when you were writing your program or if you screwed up when you were writing your type, but these don't match. Go figure out what you did wrong and fix it. So it's this self-check that we can do on our own code. On the Haskell website, there's this search engine called Hoogle. And you can provide a type to Hoogle, and it will give you back all of the code in the Hackage repository that matches that type. Okay? If you search for list of int to list of int, you get back the identity function, of course. You get back reverse. You get back a shuffling thing. You get back a sorting thing. And all of those have the same type signature. Imagine if you could do Hoogle, but use behavioral types, where you can specify security properties, where you can specify computational complexity. I want something that runs in n log n, not n squared. Where you can specify any of these interactions that it only runs in this particular namespace, so I can guarantee that it's not going to send messages anywhere else. If you could query this, what sorts of things become possible? One that we thought of was dynamic linking. You get a code repository, open source code. The authors say that they are willing to license that code to anyone who wants to link it. The linker service is a paid service, so anyone who wants to link in this stuff pays to use it, and all of a sudden you've got a new way of monetizing open source software. Another thing that you might do is if you look at the stochastic Pi calculus, if you're trying the same idea with biochemical processes, what happens if you can make a query that represents a small molecule? And the query is that when this small molecule is in this concentration in this cellular system where you've gone and described the behavior of of human cells in detail, that this particular undesirable outcome doesn't occur. Well, now you are querying databases of molecules for potential cures. We get an enormous amount of benefit out of these structural and behavioral types. Now, I'm not claiming that it's easy to type check these programs, right? Who knows if it's even decidable, but at least it becomes possible to write them. And then there's a new business opportunity for distributed type checking. If we have these practical questions that we need to ask about a database of substances, then we can throw a lot of iron at it and try and type check, try and manipulate these systems until we can verify the type. That becomes a new way of looking at things. The Curry-Howard isomorphism. It's not morphing Tim Curry into Ron Howard, but Curry and Howard were two logicians in the early 20th century, and they both realized that the idea of a type is that it's a formula. It is a proposition about other terms, about terms in the calculus. And so realizability says that we want to take some formula on the left and figure out what collection of terms that corresponds to. Here's the structural type stuff we saw earlier. So if we think of terms in the programming language as products, that is, they're pairing up their subterms together, and collections as sums, right? A set, you can add things to the set, so that's something like addition. Then what we have is a distributive law is a way of going from products of sums to sums of products. So in the structural types, we have this string thing here down at the bottom. We can think of that as the sum of all strings. And then the JSON around it is the product. So what is the set of things that match this pattern? Well, we do the distributive law. We take the product of sums into a sum of products, and the products that are being summed together are the specific instances of the JSON structures, all collected together into one big collection. So this is the question of realizability, and the distributive law is what we can combine with monad laws. So if we've got a term calculus that is some way of expressing a programming language and its operational semantics, call that monad T, and we have a collection monad, lists, sets, trees, some notion of collecting these things together, and a distributive law, then we automatically get realizability. We start with this thing on the left that has, two levels of JSON and then a type identifier within type identifier and so on. And then we use the monad laws to collapse the two T's and the two C's together. Then we use the distributive law to swap the first T and C. And then the monad law again. Eventually, we'll necessarily get to CTX on the right-hand side. That is a collection of terms. So starting from a structural type, we have this way of getting over to the thing that it means. And so that gives us a way of automatically, for any programming language where we have a formal operational semantics, that is, if you've got a VM for the thing, or a description written in something like mod or K, then we can transform it in this way and derive a type system that is designed for that particular language. And then you can use the stuff built into K for saying, if I've got something over here that satisfies this semantics, and I've got something over here that satisfies this semantics, if I've got a program here and a program in a different language over here, and then I want to combine them, what happens, right? I can add together two term languages. If I've got a domain-specific language, Scala makes it really easy to write domain-specific languages, but sometimes they're just crammed in there together like HTML and JavaScript, right? Given two of these things, the way that Greg Meredith first encountered this problem was that he was able to tile an ASIC with Pi calculus machines, because it was a very simple thing. But then the question is, okay, how do we shuttle messages around between them? There's no notion of locality in Pi calculus. So he's like, well, what happens if we use the ambient calculus, which is all about locality, moving things in and out of these membranes? Well, now he has no type system for it, right? You may have a type system for one or the other, but how do you do both? Well, after about a decade, he worked this out, and I helped him formalize it. But now you can combine programming languages and derive a new type system tailor-made for the operational semantics of that programming language. And then you can use the behavioral types and the rely guarantee stuff and reason about how it behaves, even if it's not functional, and get some kind of guarantees about how this system is going to behave. So that's what we've been working on at Pyrofex with our chain. We're really excited to see what people do with Rolang and with these other generalizations of Pi calculus, and encourage you all to get involved. And thank you very much for your time. Any questions? Yes?
In the slide on behavioral type,
Yes?
the parameter k, is that just a stand-in for?
It's any term context. So a term context is a program with holes in it, right? That says right here we're going to fill something in. Don't know what it is yet. So then when you take a term context and you fill it in with t and u, then this rewrite says, when I've got a term of this shape, it rewrites to a term of that shape.
Okay, so the type of row is a substitution of u for t?
The type of row is an edge in this graph between terms and reductions. So in this case, it's saying, if there is, I want those terms t such that for all terms u, when I put them into this context and form some node in this graph, that all of the edges going out of the graph, that's the rows, end up with things of type y. And so if I've got the x, then I'm guaranteed to get to a y. Any other questions? Yes, in the back.
Can you talk about how you're using the Scala? Is it to implement the DSL for the language, or could you talk about that?
Sure. The question was how we're using Scala. All of the code we are writing to implement the platform is in Scala. So the interpreter, the interaction with the file system, let's see, we've got the Rolang team that's writing the contracts. They're not necessarily using Scala, though we wanted to hire Scala devs because anyone who can learn Scala can learn this stuff. There's the storage team, there's the networking team, all of that's done in Scala. There's the interpreter language team. And then Greg Meredith also gave us an imperative 1990s C++ implementation of a VM that he had written and wanted us to convert it to functional Scala. And so there's a team that has been working on doing that so that we can compile it down to bytecode and perhaps make it run faster than the interpreter would. So we've got those three different teams using Scala. Yes?
Have you been thinking about the problem of pricing storage in terms of like smart contract state and code, and the problem of kind of a one-time fee that's in place right now?
Yeah, so the question is, have we thought at all about pricing storage? We have. The current model involves paying a periodic fee for storage, that you pay so much to store it for a particular amount of time. And then after that time, if the wallet is empty that you paid for the thing with, it'll deduct it until it runs out of money or the time limit is up. If it's empty, then it will remove that from the state of the system, issue a hash of the code that was removed. And then later, if someone wants to revive that, they can come back with code that matches the stuff that was removed, a new wallet to pay for it, and a proof that it hasn't been revived before. So that's our model of managing storage. For managing other things, we have a notion of linear pre- and post-conditions. So that's an extra thing beyond the behavioral types that I didn't talk about here. But the idea is that someone who is wanting to pay for the execution of some code says, I need these other things to already exist in the blockchain. And so I will pull them in, and then I will pay for my code acting on those. And so it executes in its own little isolated blockchain until it's done. And then the linear post-conditions pull out stuff from the result. And if there's nothing left over, everything matched up properly, and we commit that transaction. Otherwise, that transaction never occurred, and it continues on. And so these linear pre- and post-conditions are also a kind of type information that we can combine together and guarantee behaviors. And so it also lets us delimit who's going to pay for what. In Ethereum, it is always the message sender that pays for the execution of the contract. Here we wanted to be able to support, say, a data feed, right? I'm willing to store the data on the blockchain, but I'm not willing to pay for its processing. But sending a message, doing a pi calculus send operation is the same either way. And so by using the pre- and post conditions, I can say, I am not importing anything. I am merely deploying this, and I expect what I deployed to be the only thing left over. And so that delimits how much I am paying for. I'm paying for the storage of the output. On the other hand, if I do want to send a message and pay for it, then I import the contract that I'm going to execute, do the deploy, get the stuff out, and say what I expect to be left over, and I'm willing to pay for that processing. So that's how we're doing the pricing in our chain. Yes?
So like one thing that all next generation blockchains are promising is like focus on transaction throughput. And so I was wondering like how, like one way of solving that is through consensus mechanisms, speed ups, but another way is through like this kind of namespacing where you can sort of tell like what contracts can talk to other contracts and how the execution flow happens, like what can you parallelize, what can you shard, just because you know what's happening with this kind of namespace messaging passing. So
right, so the question is about throughput and how sharding and namespacing comes into play. There's this fundamental trade-off between distributed computation, that is taking a problem, chopping it up into a bunch of different pieces, and handing those out to be processed. And each one expects to get a different answer, and then you get it back. And verified computation, where you give the same thing out to a bunch of different computers and expect all of them to have the same answer when they come back. Right? The blockchain is all about verified computing as it currently stands. But we need, for throughput, to get some distributed computing going on in there too. And so there are two different ways of doing that. One is a way that works but ends up being centralized, and so is not as desirable for that reason. If you have big players, say I'm a hardware owner, I've got 1,000 machines, then I can send different things to different computers. They're all running in their own namespaces. And I don't have to check the work of any of the other computers in my network, because I trust them. By extending this wall of trust around my computers that are operating in all these different namespaces, I can reduce the communication load. And then you have 4 or 5 big players who are doing that, and we're all pretty much in the same namespaces. We trust each other not to trust each other. We believe that these other players aren't going to collude against me because their interests aren't aligned. So then we get some notion of validation out of each of those namespaces. But that's a very centralized way, right? If the government came in and said, you're going to shut down all 1,000 of those computers, you can't continue operating as a business in that country unless you obey the government. So that has to happen. The other way that we're doing is having lots of independent copies of the RChain blockchain. And the way that they interact with each other is that the validators of one are clients of the other blockchain. And so the validators here have wallets and money in this other one. And so if you have 2 of them that are both sharing this parent chain, This one says, I want to send you some money. So then we use a timed hash lock contract. That is, a guy here, Bob, says, well, here is a hash of a secret I know. Then Alice says, I'm willing to pay parent so much money in this parent chain. I'm willing to transfer that to you if you can present me with the preimage of this hash. And then this guy says to Bob, well, I'm willing to transfer this much money over into this other account if you can present the preimage. And then Bob, of course, knows the preimage, so he publishes it, and then everybody sees that and can claim their money. In order not to lock up funds if Bob just hangs on to his preimage for a long time, then you have a time limit that says after this point, nobody can claim any funds. But this allows transfer of value from one over to another. It comes at the cost of not being able to trust any of the code that is sent to you. So whereas within a particular blockchain, we have unforgeable names. These behave very much like Java references, that even though they are implemented on the hardware as pointers to some object in memory, there's no way to take an integer and turn it into a Java reference, right? You have to have been passed that reference in order to cause any side effects by means of it. So we're using the object capabilities security model within a blockchain. But between blockchains, they have to act exclusively as clients, which means they can't mention by name objects within the blockchain. What they can do is refer to well-known registries and say, here is an identifier, here's a public key, and then it goes and looks up the appropriate reference that you ought to communicate with that point, that you ought to communicate with from that point on. So there's this way of chopping it up into lots of independent blockchains. They're not validating each other's work, but that's the price of distributed computation. So we have two different ways of achieving the sharding. We think it's a reasonable trade-off between them. Yes?
You mentioned about linear pre- and post-conditions. It sounded very dynamic, but Greg had written a paper about linear types and state in blockchain. Is there any relationship there?
Yes, certainly. The for construct only pulls one message at a time off. You can encode replication. In Rolang, we just include it. We also include new. It's a friendlier language. But there's still this linear discipline of being able to put one message that will be consumed by one for. And that lets you do things like get a lock. You simply grab a message that's on a channel, and only one guy can grab it. And then when you're done processing, you put it back. And so that's a very simple application, getting a lock on a resource. So these linear types let you reason about how these resources are consumed. Yes?
Is that also through capabilities, or what's the...
So object capabilities is another discipline similar to functional programming in that both of them are trying to reason about side effects. The way functional programming does it is there are no side effects. You wrap everything up in a monad and you only get side effects at the one point where you run the monad. Object capabilities says the only way you can cause side effects is by means of references that have been passed to you. So unless you receive a file system object, there's no way to communicate with the file system. And so, right now, if you are on Windows, you can pull up Solitaire, and it has all the authority you do. It could overwrite your hard drive if you download some arbitrary Solitaire. That's the source of much of the source of many of the malware problems that Windows has. But if your text editor has to be passed a file object, and the only way to get a file object is to tell the operating system, hey, I need a file object. So the operating system pops up a window and says, please select a file. You choose it, and then it grants that one file handle to the program. Then you can limit its authority to cause side effects by saying, this is the only thing I designated, therefore it's the only thing that can possibly be affected by this code. So the object capabilities paradigm is make sure there's no ambient authority, there's no built-in stuff, except at the very start where you run it, and then you hand off references to the things that you want it to be able to affect. So we've taken that same approach here in Pi calculus. Since it's not, or row calculus, it's not a functional programming language, but at least we can use this object capabilities discipline to reason about the side effects that code can have, plus these linear pre and post conditions for reasoning about the price that will be paid for them. Yes?
Can you say a little bit more about the modeling of nondeterminism? You showed how in the Pi calculus you can have a term that resolves in two different ways. And if you explained it, I missed how you resolve that. You just try to avoid that when you're...
Oh, you may not want to. So for instance, if you want to do leader election, say you've got a whole network of computers that are agreeing on this stuff. It's doing the blockchain computation. But then you want to get some data off the web. You want to read a counter, right? If all of those computers go and hit the same web counter, they're all going to get different answers. So you elect one of your group to go and hit the web counter and then just come back and tell what happened. There's no way to verify what he did, but somebody's got to be chosen, and it's not going to be everybody. And it matters which one gets chosen to go do that on your behalf. Sometimes you want races, right? First one to give me this information gets the reward. So these race conditions aren't always undesirable, but you want to be sure that you don't have them when they are not desirable, right? So the behavioral types are our approach to saying, we don't want a race condition here, here it's okay. Great, thank you very much for your interest.